This is SAT Math Manual, Section 14, Exponents and Radicals, where we will, of course, discuss exponents and radicals. Most of this information, as is true of many of the concepts on the SAT, this information should just be review for most students. There are some advanced exponent and radical concepts, for instance, negative exponents, rational exponents, but again, by the time students are in their sophomore, junior, senior year, most of these rules will have been encountered and reviewed in quite a bit of detail. So again, hopefully most of this is review. We are going to try to move through this rather quickly. Basic exponent terminology and rules before we get into this, just so that when we are going through the rules, we know what all of the terminology refers to. So first things first, when we have an expression like ax to the n, for instance, something like 3x to the fourth, the a, the 3, those are the coefficients. So a is the coefficient. X, yes, it is a variable. However, when we are dealing with exponent rules, when we have a variable that is underneath an exponent, we call that variable the base of the exponent. Do keep in mind there can be numeric bases as well. For instance, in 4 to the 5th, 4 would be the base, 5 would be the exponent. So the n here, the 4 here, the 5 here, those are known as the exponents. Occasionally, we may refer to those as powers as well. So coefficient, base, exponent, important to know what those are, what positions they occupy. In terms of the basic exponent rules, what I would do here is I would pause the video and I would run through all, 10 to 15 of these examples. That is, of course, if you feel solid with your exponent rules. I am really just going to run through these. I'm not going to go into too much detail about the rules. I may briefly describe them, but if you do want to pause the video, or even after the video, just go back to this page and make sure you read through the rules and the illustrations and make sure all of your examples are right. That's a good idea. So in terms of the exponent product rule, we just have to have the same base, and if we have the same base, we can add our exponents and multiply our coefficients when we are multiplying terms. So again, when we're multiplying terms that have the same base, we do have the same base here in this first example, we simply add our exponents, multiply our coefficients. Adding exponents, we get r to the 6th, that's 4 plus 2. Multiplying the coefficients, we get 12. So this is 12r to the 6th. When we have numeric bases, 2 to the 8th times 2 to the 3rd is simply 2 to the 11th, not 4 to the 11th. Again, we do not multiply our numeric bases. In this right-hand column here, you have some mistakes to avoid. This third example, a lot of students are unclear on what we want here, but what we're actually doing is we're doing an example that illustrates this illustration. What we are going to do is we're going to deconstruct 5 to the x plus 2 into 5 to the x times 5 squared. Remember, if we have the same base, which we do, 5 and 5, we add the exponents. So 5 to the x times 5 squared would be 5 to the x plus 2. We are simply deconstructing 5 to the x plus 2 into 5 to the x times 5 squared. 5 squared, of course, is 25. So we could rewrite 5 to the x plus 2 as 25 times 5 to the x. 25 times 5 to the x. Again, just a little deconstruction. Once again, before we proceed, just want to make sure you understand, if you are unclear on any of these examples and how we got the answers that we got, I would come back here after the video, make sure you look over the rules, the illustrations, the examples, the mistakes to avoid, and certainly if you are still unsure about anything, you must seek additional help, either from your tutor or from other sources, other resources, maybe the homework, maybe other videos. For the quotient rule, when we are dividing terms with the same base, what we do is we subtract the exponents and divide the coefficients. So we have 6 to the 8th divided by 6 squared. This is just going to be 6 to the 6th. Again, we simply subtract the exponents. Do not divide your numeric bases. In the same way that we don't multiply our numeric bases, we do not want to divide our numeric bases. 6 is not a coefficient, it is a base. When we do have coefficients, we do divide those coefficients. So this is 32 divided by 4, which is going to be 8. I'm going to keep that 8 up there in the numerator. x to the 8th divided by x to the 4th, that is going to be, we're not going to have a denominator here, are we? We're going to have x to the 4th and then y to the 10th divided by y to the 5th. Subtracting 10 minus 5, we get y to the 5th. I'm going to get rid of that fraction bar because we don't need it. The denominator goes away here. Be very careful of dividing your exponents. 8 to the 4th, x to the 8th divided by x to the 4th is not x squared. Similarly, y to the 10th divided by y to the 5th is not y squared. Do not divide your exponents. You subtract your exponents. The exponent power rule, this is otherwise known as raising a power to a power, or the parentheses rule, where we have an exponent inside parentheses and an exponent outside parentheses. In short, what we need to do is distribute that outside exponent to all of the inside exponents, even those exponents on a coefficient. So you can see that in the second illustration here, that a is a coefficient. If you say that a to the first is your coefficient, you would need to distribute that p to both the n and the exponent on the a, whether it be a 1 or a 2 or whatever it is. So let's go through these. Again, outside exponent gets distributed or multiplied by all of the inside exponents. So we've got x to the 12th. We've got y to the 24th. That's 6 times 4. And then 6 times 3, of course, is 18. Z to the 18th. I would encourage you to do all of this without your calculator. Be careful of adding the exponents. Remember, what we are doing here is not the same as what we were doing up here. When we are raising a power to a power, we multiply. We do not add. So do not add your outside exponent and inside exponents. Here we do have a coefficient, so we need to distribute that outside exponent. So we get 2 to the 4th, t to the 4th. 2 to the 4th is 16, so this would be 16t to the 4th. Now here it appears that we can't do anything because we do not have the same base. We said up here for the exponent product rule that if we wanted to multiply two terms, we have to have the same base and we could add the exponents. However, in this case, we can actually apply this rule over here, this illustration of the rule. What we can do is, again, we can sort of go backwards, I guess. We can imagine that 2 to the 3rd times 5 to the 3rd came from 2 times 5 to the 3rd, right? Because we would distribute that outside exponent 3 to both the 2 and the 5, getting 2 cubed times 5 cubed. But if we go in the other direction, in this direction, we can combine the 2 and the 5, the product of 2 and 5, as our base up to the 3rd, and therefore 2 to the 3rd times 5 to the 3rd is 10 to the 3rd. And indeed, we can do that whenever we have different bases but the same exponent. So, if I had 3 to the 7th times 6 to the 7th, again, I could imagine that that came from 3 times 6 to the 7th, which means 3 to the 7th times 6 to the 7th. I chose numbers that are very, very tongue twisty. 3 to the 7th times 6 to the 7th could be written as 18 to the 7th. Next time I won't choose 3s and 6s and 7s. 121x squared, again, doing something fairly similar here, a little bit of a deconstruction. That 121x squared, 121 can be written as 11 squared. We are multiplying by an x squared. So again, we have the same exponent but different bases. We can combine those bases together as a single base, or the product of 11 and x as a single base. So I could write this as 11x squared. Not very different from what I did in the previous example. The next example is here just to make absolutely sure, probably one of the most important things here, because it's one of the most common careless mistakes that students make. When you are adding or subtracting terms inside a set of parentheses and you've got an outside exponent, you cannot distribute that exponent to each of the inner terms. You can distribute the exponent to the inner terms when the inner terms are being multiplied, but not when those inner terms are being added or subtracted. So parentheses x plus y and parentheses squared is not equal to the first term squared plus the second term squared. What you would have to do here is a process known as FOIL, which all of you should be familiar with. I'm going to write the work down here. So this would be x plus y times x plus y. First terms, x times x is x squared. X squared. Outer terms, x times y is positive xy. Inner terms, y times x. I'm going to write that as another xy. And last terms, that's first first terms, outer terms, inner terms, last terms. That's what FOIL stands for. The last terms, y times y is y squared. So all of this becomes x squared plus 2xy plus y squared. I really hope all of you are familiar with that process by sophomore, junior, senior year. 2 to the 2n, what we are going to do here, again, a little bit of deconstruction. I am going to take 2 to the 2n, and I'm going to make it into 2 squared to the n. Remember that if I had something like 2 squared to the n, I would be distributing that outside exponent to the inside exponent, ending up with 2 to the 2n. But what I'm doing here, once again, I'm deconstructing. I now have 2 squared to the n, which means I can write this as 4 to the n. 2 to the 2n is exactly the same as 4 to the n. And then finally, we have a quotient inside our parentheses here. Nothing too surprising here. We're going to distribute that outside exponent to the inside exponents. There is an inside exponent of 1 here. We distribute the 3 to that 1 as well, and we get d to the 6th divided by 5 cubed, or 125. You can write it either way. So those are the basic exponent rules and a bunch of examples. Hopefully everybody was familiar with how to do those again for the third or fourth time. If you're not, you got to make sure you are. So come back here, review these rules, make sure you understand why all of these answers are what they are. Down at the bottom of the page, we've had some practice with simplifying terms. Let's actually solve an equation with a bunch of these exponent rules. I would pause the video and try this question on your own. It is a calculator question. So you can use your calculator, of course, but you probably shouldn't need to. So for all values of x such that x does not equal 0, what value of b, that's what they're asking, value of b satisfies this equation. So we're just going to take a look at this, and we're going to start applying a bunch of the exponent rules that we just went over up above. First things first, probably let's keep that x squared on the left, but let's distribute this outside exponent to both of our inside exponents. So this is going to be times 2 cubed, which is 8. You can do that in the calculator if you need to, although you should be familiar with the cubes of the first few integers at least. So the cube of 2 is 8, and then x to the 4th to the 3rd is going to be x to the 12th. I am multiplying those exponents. Over there on the right, again, applying some of our exponent rules, the coefficients get divided. I end up with an 8. 24 divided by 3 is 8. Can do it in the calculator if you need to. And then x to the b divided by x to the 4th, we have the same base, so we're going to subtract our exponents. We get x to the b minus 4. Over here on the left, doing a little bit more on our exponent rules, we have two terms that we are multiplying that have the same base, so we're going to add the exponents. So we get 8x to the 14th equals 8x to the b minus 4. We divide both sides by 8 to get those two sides cleaned up a little bit, get rid of the 8's. We have x to the 14th equals x to the b minus 4. And there is a rule when we have two sides of an equal sign, both of which have the same base, we can drop the base. We're going to talk about this in just a few minutes. We can drop the base and set the exponents equal. So now we have a nice simple equation with which we can solve for b. We add 4 to both sides. We get b equals 18. Is that what they were asking? Yes, it is. And we are done. So b must equal 18. At the top of the next page, we have some basic radical terminology and rules, just like we did for exponents. So let's talk about a term like the nth root of x. The root symbol is known as the root symbol, or more formally perhaps the radical symbol. The x, which is the item underneath the square root symbol, is known as the radicand, and the n, which is the root or the index. The index or the root. Will you see terms like radicand, index, radical on the test? Probably not, but in order to go through these rules, we have to have a way to name each of these items. So now you know what they are named. By the way, when you do not see a index written, when you just see something like root 7, there is an unwritten 2 in here. In other words, you are taking the second or square root. So when there is no index written, you are just dealing with the square root. Here you would be dealing with the cube root. Here you'd be dealing with the fourth root, and so on and so forth. The basic rules and a bunch of examples. Again, we're going to do this the same way. I'm just going to run through these as quickly as humanly possible. I would suggest pausing the video and trying these on your own and then coming back and joining us if anything doesn't make sense to you. As I've said several times, make sure you review this, make sure you talk to your tutor, make sure that you seek out other resources to get further practice and to become more confident with this stuff. So we are going to first talk about adding and subtracting radicals, and the way that we do that is as long as we have the same index and radicand, as long as we have the same number in the little nook of the radical, and here we have unwritten numbers, which means we're dealing with square roots, and we have the same radicand, we have 5s in both cases. When that happens, we can simply add the numbers in front of the radicals. I guess you could sort of think of them as coefficients. So we have a 2 root 5 plus 5 root 5. That means we are dealing with 7 root 5s. 2 root 5s plus another 5 root 5s, 7 root 5s. Be careful, do not add the numbers under the radical. Do not add the radicands. Over here, again, we have the same index, an unwritten 2. We have the same radicand, the x's. We have a 1 in front of the first root x. So this is 1 root x, take away 4 root x's. That leaves us with negative 3 root x's. In terms of this note down here, very important, do not add radicals with different radicands. If you have different radicands, there's really nothing you can do except possibly enter this into the if you're on the calculator section, you could enter this into the calculator and get a decimal value. You will probably never need to do that on the SAT. Square root product rule. This is a very important rule. This actually shows up in several different places. Complex numbers is one of them, where we can rewrite the square root of a product. So notice we have the square root of a product. We can rewrite that square root of a product as the product of the square roots of the individual factors in the product. So root AB can be written as root A times root B. In other words, we can separate the A and the B out into their own radicals. I do want to jump over here before we do these examples and just say that this rule does not apply when you are adding or subtracting terms inside the radical. In other words, you cannot rewrite root x squared plus y squared as root x squared plus root y squared and get x plus y. That is not allowed. That has never been. I shouldn't actually put that equal sign there. What I should do is I should say that you cannot go from here to here to here. That is not allowed. Don't do that. If the terms are multiplied, okay, if you have x squared times y squared and you want to then separate the x squared and the y squared into their own radicals and then end up with xy, that's fine. Multiplication, perfectly fine. Addition, not fine. So what we are going to do in this case is we are going to separate this radical 16x squared y to the fourth into root 16, root x squared, root y to the fourth. So let me actually just, why don't I just write it in there? So root 16 is 4, root x squared is x, and root y to the fourth is y squared. Y squared times y squared is y to the fourth, so the square root of y to the fourth is y squared. So we can simplify root 16 x squared y to the fourth into 4xy squared. Similarly, we can go in the other direction. We can take two things that are being separately multiplied in their own square root symbols, and we can combine the radicands under the same square root symbol. So instead of having to deal with what the square root of 18 and what the square root of 2 is, what we can do is we can simply put the two radicals, put one radical over the two radicands. Radicands are multiplied. We get root 36. Everybody should know that the square root of 36 is 6. We will talk about this in a moment, but just so you know, when you have something like root 36, the only possible answer is positive 6. Root 36 means the principal or positive square root of 36. The only way that you would want to include plus or minus 6 is if you had something like this. If you were solving, in other words, solving for a squared variable, when you square root both sides of this equation, then yes, you do have to account for the fact that x could be one of two values, 6 or negative 6. But if you were just given the square root of 36, you are only talking about the positive square root. That is the mathematical rule, mathematical convention. The square root quotient rule, very similar to the product rule. We can combine radicands. We can split radicands. So root a over b can become root a over root b. Root a over root b can become root a over b. So in the case of this first example, instead of dividing 16 by 49 and getting some fairly ugly decimal, what we can do is we can simply separate the numerator and the denominator into their own radicals. So this would be root 16 over root 49, which is simply 4 over 7. Again, if you want to use your calculator here, you can, although I would suggest knowing how to do all these without the calculator. And again, here, instead of worrying about what the square root of x to the 5th is and what the square root of x cubed is, why don't we just combine x to the 5th, x cubed under one radical, and then we will apply the rule that we learned on the previous page. Same base, different exponents, we're dividing, so we subtract the exponents and we get root x squared, and the square root of x squared is x. So again, we subtract the 5 and the 3, we get a 2. Square root of x squared is x. Squaring a square root, we should understand that when we square a square root, basically the radical just goes away and we're left with only the radicand. So the square root of a squared, the square root of a squared is a. So the square root of rs squared is rs. And down here, what do we have? We have another more general variation of this rule, where if your index and the exponent or power outside the parentheses are the same, anytime that case is true, here we had a 2 and a 2, those two were the same, the index, the exponent, the power, the n and the n are the same, then the radical just goes away, and again we are left with a bare radicand. So the cubed root of 5.72 cubed, index, exponent the same, radical just goes away and we're left with the radicand. Doesn't matter how ugly that number gets, we are just going to be getting rid of the radical. Occasionally we need to simplify radicals on this test. Usually we're just going to be dealing with square roots, but we might occasionally need to simplify a cube root. Everybody has different ways of doing this. Some people use prime factorization, a lot of different methods for this. We are going to use a method in which we basically are going to factor the radicand into a product containing as many perfect squares as possible. That's what it says here in step 1. So what does that look like? Here's the example. What I'm going to do is I'm going to say, okay, well, 48 can be broken up into 16 times 3. Why am I doing that? Because 16 is a perfect square. That's what I'm trying to do. Could I use a 4 to go into 48? Yes, I could. 12 goes into 48 4 times, so I could do 4 and 12, but then I would want to take the 12 and start breaking the 12 down into its perfect squares as well. I chose to do 16 because 16 is the largest perfect square that goes into 48. So the 48 is 16 times 3. The x is going to be x to the 4th times x. X to the 4th is a perfect square. And then the y is going to be, the y cubed is going to be y squared times y. So again, there's a perfect square there, there's a perfect square there, and there's a perfect square there. Now what I'm going to do is I'm going to write that radical expression as a product of radicals. What I mean by that, I'm just applying a rule we just talked about above. So I'm splitting all of these factors into their own radicals. So there we go, there we go, there we go, and there we go. So every one of those products now has its own radical, and now I can start simplifying the ones that can be simplified. This is 4, this is x squared, this is y. So square root of 16, square root of x to the 4th, square root of y squared, and then all of the radicals, they just need to stay, all the, I should say, radicals or roots of non-perfect squares, they need to stay in their square roots. And now I'm going to combine these three guys on the outside for x squared y, and these three guys will go back into a single radical. They will get back together under the radical sign. Oh, it's so sweet, they got back together. So that is the way that we tend to recommend to our students to break down square roots, to break down radicals. If you have your own way that works for you, fine, keep using it, but this is a way that tends to be fairly reliable and efficient and simple. At the top of the next page. At the top of the next page, we deal with rational, otherwise known as fractional, and negative exponents. These types of questions, this particular variation of exponents and radicals is very common on the test. When exponents and radicals are tested, very frequently the exponents will be fractional and or negative. So with rational or fractional exponents, we do need to understand what it means to talk about a term like x to the a over b, as we have here. So again, we have a rational or fractional exponent here. The base obviously is the x. That's the term underneath the exponent. The a, the numerator of the fractional exponent, of the rational exponent, the numerator is a power, or just sort of a regular exponent, and the denominator is a root or index. So what that means is, if I see a term like x to the a over b, do want to just reiterate, this should be review for most students. The x to the a over b can be written in one of a couple ways. We can raise the x to the a first, so there's the exponent or power, that numerator, and then take the b root of x to the a, or we can take the b root of x and raise to the a. So again, in either case, you can see that the a, the numerator, is in the exponent position, and the b, the denominator, is in the index or root position. So whatever that denominator is, that's your root, and whatever that numerator is, that is your exponent, and all three of these terms are exactly the same. They are just written in different forms, one in exponential form and the other in radical form. So what we're going to do in example 2, if you are familiar already with rational or fractional exponents, I would obviously, what did I just do there? I would obviously recommend pausing the video and trying these examples on your own. So what we are going to do here is we're going to write these terms as a radical expression. So x to the 3/4, again, we can write this in one of two ways. I'm just going to go ahead and write it on this line. We could do x cubed and then take the 4th root. Okay, so again, numerator is the power, numerator is the power, denominator, the 4, is the root, or we could take the 4th root of x and then cube the whole thing. Either of those are acceptable answers. With 8x cubed to the 2/3, we've got a little bit more work to do. Again, remember, we have this situation where we have the outside power. We have to distribute that outside power to both of the inside powers. So this is going to become 8 to the 2/3 times x to the 3rd to the 2/3. Remember that 2/3 times 3, 2/3 times 3, the 3's cancel and we get 2. So this just all becomes x squared. Now for that 8 to the 2/3, there are two ways we can go about this. We can square the 8, get 64, and then take the cubed root, which is 4, or we could take the cubed root of 8, which is 2, and then square the 2, which is also 4. How do I want to write this out? I'll just do the, let's do this. Let's do cubed root of 8 squared times x squared. So I'm going to cube root 8 first, and then I'm going to square the result. Cubed root of 8 again is 2. We square the 2 times x squared, and we get 4x squared. So the answer to example 2b is 4x squared, 4x squared. Again, you can apply the power and the root, the numerator and denominator of the rational exponent, in either order, but you will find in many cases, especially when you're not allowed to use a calculator, that one order is probably better than the other, mainly because the other order might end up requiring that you calculate very large values, and without a calculator that can be tough. For instance, if we have 25x squared to the 3/2, so again, what we're going to do first, we will distribute that outside power to the inside power, so 25 to the 3/2 times, again, x squared to the 3/2, the 2 times 3/2, I'm just going to write this up here, 2 times 3/2, the 2's will cancel and we'll end up with x cubed there. So this right here, what I was saying before is we could cube the 25 and then take the square root. If you know what 25 cubed is, more power to you. If you know what the square root of 25 cubed is, well, then you're a genius. What I would do here is I would take the square root of 25 first and then cube the result. So again, what that means is I'm going to take the square root. I don't need to write the index 2 there, but I'm going to anyway. And then I'm going to cube that result, x cubed. The square root of 25, of course, is 5. 5 cubed times x cubed. We could write this as 5x cubed, but we are going to write this as 125x cubed. I said a moment ago that you really should know the cubes of the first few integers. That would include going up to 5. You should know that 5 cubed is 125. So this is example 3a, 125x cubed. Example 3b, we've got 1/9 to the 3/2. So what am I going to do? I'm going to go ahead and distribute that outside 3/2 to both of those inside ones. So we get 1 to the 3/2, which is just 1. I'm not going to waste any time writing the 3/2 there. 1 to any power is just 1. Over 9 to the 3/2. And again, I need to determine whether I want to square root 9 and then cube the result, or I want to cube 9 and then square root the result. I want to do what I did up here. I want to square root 9 and then cube the result. So I end up with this. And that is 1 over 3 cubed. Square root of 9 is 3. 3 cubed is 27. 1 over 27 is the answer to example 3b. At the bottom, what we are going to do is go in the opposite direction. We're going to go from radical form to exponential notation. So again, probably want to pause the video and try example 4 on your own if you are feeling confident with this stuff. If not, just watch me work through it. What value of A satisfies the equation above? So what I am going to do here is I'm going to take the term on the left-hand side of the equal sign, and I'm going to make that term into an exponential term. So the 7, remember that power, that exponent, is the numerator of my rational exponent, and the 3, the index or root, is the denominator. So on the left side of this equation, I now have x to the 7/3. On the right side, I still have x to the 2a. As I mentioned before, when we have same base, different exponents, we can just drop the base and set the exponents equal to each other. So we get 7 over 3 equals 2a. Multiple ways we can go here. I'm going to imagine this is just a cross multiplication opportunity. 1 times 7 is 7. 3 times 2a is 6a. So I get 6a equals 7. I divide by 6, and I get a equals 7/6. That's what they were asking me, so the answer here is 7/6. By the way, a note up above here, do keep in mind that anytime you see, this is just this little more notes over here, x to the 1/2, remember that is x to the 1, and the index is 2. So really what you're talking about when you say x to the 1/2, or when you see x to the 1/2, is just the square root of x. And similarly, x to the 1/3 is the cubed root of x. So again, x to the 1/2, square root of x. X to the 1/3 is the cubed root of x. Again, most of you should have already known that. Just wanted to make sure. Top of the next page, we've got to talk about negative exponents. As I said, negative exponents are reasonably common on the test. You will need to know how to handle these quickly and confidently. There's 2 ways to think about simplifying negative exponents. There's the reciprocation method, there's a relocation method. I would know both of them just so that you have as much flexibility as possible on these questions, but if one of these methods tends to click more with you, or you tend to use one method exclusively and it works for you, well, then go ahead and keep using that method. The reciprocation method. So basically in the reciprocation method, we are imagining that the negative on the exponent, the negative sign on the exponent, means reciprocate the base. So a term like x to the negative n, we can rewrite the base x as x over 1. And then again, that negative would mean reciprocate that base. So the x would go to the denominator, the 1 would go to the numerator, and the exponent would become positive. So x to the negative n could be written as 1 over x to the positive n, could be written as distributing that outside exponent, 1 to the n over x to the n, which finally could be written as 1 over x to the n. That is the reciprocation method in a nutshell. Obviously, if instead of your base being just a single number or single variable, but your base being a fractional base, it's probably even simpler. You just reciprocate the fractional base, apply the outside exponent, and x over y to the negative n becomes y to the n over x to the n. The relocation method has to do with, it's again very similar to the reciprocation method, but the relocation method basically has to do with moving terms that are in the numerator of a fraction into the denominator of a fraction and vice versa. So if we have an x to the negative n, so we have our term with the negative exponent up here in the numerator of a fraction, basically all we do is we take that term, the entire term, we move that term to the denominator of the fraction, and we make the exponent positive. If the term with the negative exponent is in the denominator of a fraction, we take the entire term, move the term to the numerator, and make the exponent positive. That's the relocation method. We're going to try some examples. Again, if you're confident and comfortable with negative exponents and you know how to simplify them and move things around and reciprocate and so on and so forth, you might want to just go ahead and do example 5, A through D on your own. So what we have to do here is we just have to write these terms without negative exponents. So for b to the negative 2, I don't know. Let's do this with the relocation method. The b to the negative 2 is up there in the numerator of a fraction, so we need to move it to the denominator of a fraction. We do need to keep a 1 up in the numerator. It's not like the numerator just disappears. The 1 stays, a 1 stays in the numerator. The b to the negative 2 goes to the denominator, and the exponent becomes positive. Just so you know, the reciprocation method would look like this. So we have b over 1 to the negative 2. We reciprocate 1 over b. Exponent becomes positive. Distribute the outside exponent to the inner terms, and we get 1 over b squared. Same answer. 3 to the negative 3. Let's do reciprocation this time. So 3 over 1 to the negative 3. We reciprocate, so we get 1 over 3. 1 over 3 cubed. Exponent becomes positive after we reciprocate. Distributing outside exponent to the numerator and denominator exponents. This is going to be 1 cubed, which is 1, over 3 cubed, which is 27. 1 over 27 is equivalent to 3 to the negative 3. Just to remind you, you're not to be using your calculator on this example, on any of these examples. The next item here, example 5c, we have got 16x squared y to the negative 1 over a bunch of other stuff. So let's take this sort of one term at a time. We'll do our constants, our coefficients, then we'll do our x's, our y's, and our z's. So 16 over 24, 8 goes into both of those. That's 2 and 3. So we're going to have a 2 up there and a 3 down there. X squared over x to the negative 4. Now do keep in mind, we actually don't even have to use what we just learned about negative exponents here. We could just subtract 2 minus negative 4 and get x to the 6, right? That's just regular old division rules. X squared over x to the negative 4. We would just subtract these two and get x to the 6th. You could do it that way, and that's why it's actually important to have as much knowledge of the different routes you can go on exponent questions, because if one way trips you up or you forget one way, you have another option. We are, of course, going to do this using what we just learned about negative exponents. In fact, we'll do the relocation method here. So I'm going to take that x to the negative 4. So I have an x squared up here. But now I'm going to take that x to the negative 4. I'm going to put it up in the numerator, make the exponent positive. The y to the negative 1, that guy is going to go down into the denominator, and the exponent is going to become positive. So now I have the y and the y squared next to it. And then the z to the negative 3, again, relocation method, the z to the negative 3, that term can just go up to the numerator and exponent can become positive. And now applying some of those other exponent rules, I get 2x to the 6th z cubed all over 3y cubed. 2x to the 6th z cubed over 3y cubed is the answer to that is supposed to be a cube. Let me get rid of that. Those are both ugly. Cubed, cubed. There we go. And that is a z, even though it doesn't look like it. Example 5D, what are we going to do here? I think reciprocation method is definitely going to be the way to start, at least. We're going to reciprocate that base. Those two guys reciprocate. We change the exponent to a positive 3/2. And again, doing what we've been doing many times, we're distributing that 3/2 to each of these inside exponents. 2 times 3/2 is 3. so that becomes x cubed. And 16 to the 3 halves, how do I want to do that? I want to take the second root of 16 and then I want to cube it. I don't want to have to cube 16 first. So this becomes x cubed over 4 cubed, which is 64. Square root of 16 is 4. 4 cubed is 64. Again, you should know the cubes of the first few integers. X cubed over 64 is the answer there. Down at the bottom of the page, we have to talk about some peculiar behaviors or properties of certain bases and exponents and roots. We will first talk about zeros and ones. We do need to know that x to the 0 is, you might want to pause the video and try all 4 of these on your own before I give these away. X to the 0 is 1. 0 to the x is 0. Okay? In fact, anything to the 0 is going to be 1 as long as x itself does not equal 0. Don't worry, you will not be tested on 0 to the 0. 0 to the x, as long as x is not 0, again, that's always going to be 0. So anything to the 0 power is going to be 1. 0 to any power is going to be 0. Now we deal with the 1s, so we dealt with the zeros, now we're going to deal with the 1s. X to the 1 is always x itself. Anything raised to the first power is always the base, is always the thing being raised to the first power. And 1 raised to any power is always going to be 1. Doesn't matter what that power is, positive, negative, 0. 1 raised to any power is always 1, and anything raised to the 1 is always the base under the 1. We're going to do one example because this should be very simple stuff, and then we're moving on. So example 6, pause the video, try it on your own. They are asking us here what the value of all of this crud is. 10 to the 0, remember 10 to the 0 is 1. 10 to the 1, anything to the 1 is just the base. 0 to the 10th, remember that is 0. We don't really need to keep going because as soon as we know we're multiplying by 0, we know the answer is going to be 0, but we are going to keep going just to get some practice with this. 1 to the 10 is 1. So again, anything to the 0 is 1. 10 to the 1, anything to the 1 is always the base under the 1. 0 to the 10th, 0 to anything is always 0, and 1 to the 10th, 1 to anything is always 1. So this is 1 times 10 times 0 times 1, and we don't really need to do much else because we're multiplying by 0, which means we get an answer of 0. At the top of the next page, we have to talk about negative bases. Negative bases can be very, very tricky for students, especially when it comes to using the calculator. There are a couple of careless mistakes that students run into. Very important to understand that if we have a negative number and we raise that negative number to an even power, we are always going to get a positive result. And any negative raised to an odd power is always going to give us a negative result. We're going to see some examples of, many examples of this in a moment, but again, if we take negative 2 and we raise negative 2 to, let's say, the 4th, we are going to get positive 16. And if we take negative 2 and we raise negative 2 to the 3rd, an odd exponent, even exponent, odd exponent, we get negative 8. So any negative to an even power, positive result. Any negative to an odd power, negative result. In terms of negative bases with and without parentheses, we do need to understand what each of these terminologies or what each of these notations means. When we see a negative x squared, what that means is that we are going to square x, which obviously means multiplying x by itself. So we are doing the square, which is, by the way, this is just PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. So we're doing the exponent first, and then we are multiplying exponent first, and then multiplying by that negative. So again, we are squaring the x, which means multiplying x by itself, and then we are applying that negative. But if we have parentheses around the negative x, what that means is we are multiplying negative x by itself. We are squaring negative x. So negative x times negative x, which of course would give you positive x squared. Two negatives being multiplied together would give you a positive. We're going to run through a bunch of examples. You can use your calculator here, but you need to understand what the calculator is doing, or more accurately what you are telling the calculator to do. So I'm going to bring my calculator up. So here's one of the most common mistakes that students will make in the calculator. I'm actually going to hold off on example 7 for a moment. Let's say you see a very simple function question where f of x equals x squared, just typical quadratic equation, parabolic equation here, and then they say, what is f of negative 2? What everybody does is they go right into the calculator and they do negative 2 squared, and without even thinking about it, they get the negative 4 and they write down, okay, this equals negative 4. That is not right. F of negative 2 does not equal negative 4, because what you should have been doing is one of a couple things. If you're going to do this in the calculator, you need to understand that what's happening is this negative 2 is going in for the x. So you are actually not squaring 2 and then multiplying by a negative, which is what you just told the calculator to do. The calculator did this right. It's not like the calculator made a mistake. You told the calculator to square the 2 and then multiply by a negative. But in the case of this function, if you are being asked what f of negative 2 is, you are not squaring 2 and then multiplying by a negative. You are raising negative 2, which is your x value, to the 2. You are squaring negative 2. So what you should have done in the calculator is negative 2 squared, and then the calculator would have given you the right answer. You also could have just known that you are squaring negative 2 and gotten positive 4. Then you also can use a store function in the calculator. I have talked about this in other sections of the manual. But if we do negative 2 and then we store the negative 2 in the x key and hit enter, and then we do x squared, the calculator will do exactly what it's supposed to do and what you want it to do. It will take the negative 2, which you have stored in the x key, and it will square that negative 2 to give you a positive 4. So let's run through these examples. Again, you definitely can use your calculator. I'm going to run through these without the calculator. If you want to run through these all by yourself, pretty much straight through to example 9 at the bottom, you can, and then come back and check your answers and your work against mine. So here, what are we doing? We are squaring 2 and then multiplying by a negative. So squaring 2 is 4, multiplying by a negative, we get negative 4. The second example here, negative 2 squared, this is going to be negative 2 times negative 2. So up here it was negative 2 times 2, square the 2, then multiply by the negative, get the negative 4. Here we are multiplying negative 2 by itself, and we are getting positive 4. Negative times negative is positive, 2 times 2 is 4. In terms of substituting a number, so this is more like what we were doing over here with this quadratic. If x equals negative 3, what is the value of x squared? Remember what you are doing here. You are taking, so they want x squared, you are taking negative 3, plugging negative 3 in for x, and squaring that value. So this is negative 3 times negative 3, which is positive 9, positive 9. If x equals negative 3, what is the value of negative x squared? Okay, so now what we are doing is this, similar to what we just did here, but now we have a negative out there on the front. So once we square that negative 3 and we get 9, this is going to become negative 9. And then if x equals 3, what is the value of negative x squared? Again, by the way, if you notice, I keep using parentheses here. Using parentheses is a very good way to keep from making careless mistakes on these questions. Just sort of think of the x as blanked out with parentheses. In other words, something like this. Whatever your x value is going in those parentheses. Up here, you got a parentheses and a square. Whatever your x value is going in here. This one, negative, parentheses, squared. Whatever your x value is going in there. So I keep using parentheses so that I don't make careless mistakes. 3 squared is 9 times the negative 1 is negative 9. If the exponent is odd, generally you're not going to have too many problems. There still can be a couple of areas of possible careless mistakes. So here, what are we doing? We are cubing negative 4. That means we're doing negative 4 times negative 4 times negative 4. Negative times negative becomes positive, but then we've got another negative hanging out here, so we know our final answer is going to be negative. 4 times 4 times 4, should know that in your head. If you need to use the calculator, it's fine. 4 times 4 times 4 is 64. 4 times 4 is 16. 16 times 4 is 64. 4 cubed is 64. Negative 4 cubed, well, we already know what 4 cubed is, so we're cubing the 4 and then multiplying by a negative, so we get negative 64 again. Down here, example 9c, we've got x equals negative 5. What is the value of x cubed? So again, I'm going to use that parentheses technique. Filling in a negative 5 there. Negative 5 times negative 5 times negative 5. negative times negative, positive. Then we've got that additional 5 hanging out there. 5 times 5 times 5 is 125, so this is negative 125. And then finally, here we have a negative, and negative 5 is going in here. We already know from up here that all this is negative 125. That's what we got on our previous question, and now we have to multiply that outside negative by that inside negative, and we get, positive 125. Positive 125. That is it for those pesky negative bases. At the top of the next page, we need to talk about negative radicands. So we've talked about negative bases, we've talked about negative exponents. Now we got to talk about negative radicands. In other words, the number underneath the square root sign. Dealing with negative radicands may result in some imaginary or complex values. It really depends on what your index is. So I'm going to, I don't need to highlight anything here. If we have a negative radicand and an even index, then we are going to have an imaginary result. Imaginary result. If we have a negative radicand and an odd index, we are going to have a real result. We will talk about complex numbers in a lot of detail in the complex numbers section of the manual. For right now, we're just going to do a couple of quick examples so that we can see how we determine whether we get a real or imaginary result. So what we are doing here is we're going to write down R or I depending upon whether we're getting real or imaginary results. For x is negative 2. So when negative 2 goes into this radicand, what happens is we get negative 3. So let me put the radical there. Negative 2 squared. So negative 2 squared is 4. Negative 3 times 4 is negative 12. So we are taking the square root of negative 12. Remember, there is an unwritten 2 in here. That is an even index. Square rooting a negative number will result in an imaginary number. So that will give us an imaginary result. Here we have got negative 2. By the way, just generally remember that you cannot take the square root of a negative number and get a real result. You will always get an imaginary result, a result with an I in it. If you know how to break this down into a complex number or into an imaginary number and you want to practice that, you can go ahead and do it right now. We don't really need to though. So what do we got here? We've got the fourth root, that's an even index, of negative 2 times negative 2 cubed. Negative 2 cubed, remember that's a negative to an odd power, so that's going to give us a negative. It's going to be negative 8. So we've got the fourth root of negative 2 times negative 8. That is the fourth root of 16. That's perfectly fine. We can take the fourth root of a positive number and get a real result. That is actually just going to be 2 there. The cubed root of x cubed, well, remember we said that, first of all, you can always have an odd index and get a real result. So we already know this is going to be real. It doesn't matter whether we have a positive or negative in here. We also did talk about the fact that when we cubed root something that is cubed, we just end up with the radicand. And if the radicand is negative 2 and we cube root x cubed and get x, we just know this is going to be negative 2, which is a real number. Negative 2x to the 3 halves. So when it comes to the fractional exponents, you do obviously need to be careful. First of all, we need to understand that the 3 halves is only applied to the x, right? We don't have parentheses here. So that 3 halves is only on the x. So what we have here is we have negative 2 times negative 2, because x is negative 2, to the 3 halves. So that's negative 2 times, remember that denominator is the root here. So we're taking the square root of negative 2, and remember that cube can go either inside or outside. I'm just going to put it inside. Well, negative 2 cubed is going to be what? Actually, let me put that on the outside. Let me do it this way, because that's actually easier to think about how this is going to work. We know right away that this is the square root of a negative number, which means we are dealing with an imaginary number here. It doesn't matter whether we cube this, doesn't matter whether we're multiplying by 2. Square root of a negative number is going to be imaginary. So whatever. Fractional bases. We do need to talk about fractional bases. They do some quirky, peculiar things. When we talk about fractional bases, we're just talking about bases that are between 0 and 1. So something like 0.5 squared or 2/3 cubed. We need to know that when we take a fraction or decimal between 0 and 1 and we raise to a power greater than 1, we get a result that is smaller or less than the original fractional base, the original fraction. We're going to look at a couple of examples here. These are no calculator examples, no using your calculator here. So 0.5 squared, you can do this in one of a couple ways. Probably the easiest way is to know that 0.5 is obviously 1/2. When we square 1/2, that's 1/2 times 1/2, which is 1/4. And again, we can see that the result, 1/4, is smaller than the original base fraction, than the original fractional base, 0.5 versus 0.25. 2/3 cubed, what are we going to do there? Let's distribute that outside exponent to each of these inside exponents of 1. So we get 2 cubed over 3 cubed, and that we end up with what? 8 over 27, and 8 over 27 is a little less than 1/3, and the original fraction was 2/3. So again, we got a result that was a smaller value than the original fractional base. At the top of the next page, solving equations with exponents. You will need to solve equations with exponents. We will talk about solving equations with radicals in a different section. We also will go into exponential equations in a different section, so we'll get a little bit more practice with some of this stuff in another section. Let's talk first about solving for a squared variable, and I mentioned this before a few pages ago, principal square roots. So we have to understand that if we are solving for a squared variable, so if we have x squared equals some value c, when we square root both sides so that we can get rid of the square on x, in other words, so we can isolate x, remember when we take the square root of x squared, we just get x. On this right hand side, we have to remember that we have to account for the fact that x could equal the positive or negative square root of c. So again, if I square root both sides of the equation to isolate a squared variable, I do have to account for 2 possible solutions. Let's do a quick example of this, and then we will move on. Example 12, might want to pause the video and try this on your own. So 3x squared equals 27, 2y squared equals 32. They want the maximum value of x minus y. I'm going to divide both sides of this first equation by 3. I'm going to get x squared equals 9. I am going to finish this out by square rooting both sides, and what happens is I get x equals plus or minus 3. In the second equation, I'm going to divide by 2. I get y squared equals 16. Square root, y is going to be plus or minus 4. Now, I could sit here and just try to think about how I can create the maximum value of this difference, x minus y. But I think what I'm going to do is I'm going to set up a little t-chart here, and I'm going to do x is 3 and 3 and negative 3 and negative 3, and y is positive 4 and negative 4, positive 4 and negative 4. In other words, what I'm doing is I'm doing positive 3 and positive 4, positive 3 and negative 4. That's these first two. Negative 3 and positive 4, negative 3 and negative 4. In other words, I'm just fleshing out all of the different possibilities here. Again, if you were able to see right away how to produce the maximum value, that's perfectly fine. I think it is important to be familiar with processes like these so that you can fully flesh everything out. So 3 minus 4 is negative 1. 3 minus negative 4. 3 minus negative 4 is 7. That one's looking pretty good. Negative 3 minus positive 4 is negative 7, and negative 3 minus negative 4 is positive 1. So it looks like the maximum value here is going to be 7. Now, with principal square roots, you do need to understand, I've said this before, when you just see the square root of some value, you do not need to account for both the positive and negative solutions. When they give you root 1 and 44 or root 81, you only need to account for the positive or principal square root of the radicand. So in this case, they're asking us for the value of x minus y. So what we do is we do x minus 12. Don't need to worry about the negative and positive. It's just 12 equals y plus 9. They want x minus y, so I'm going to go ahead and subtract y from both sides. So I get x minus y minus 12 equals 9. Add the 12, add the 12. I get x minus y equals 9 plus 12 is 21. This is a no calculator question. Don't use your calculator. X minus y equals 21. That's what they were asking, and we are done. And finally, we get to the last page of this section. Solving exponential equations using common bases. So there is another way that we sometimes will need to solve exponential equations, and that is by finding a common base. First, we need to just review something I've said a couple of times about dropping the base. No, that does not mean that you need to start playing a bunch of music in the testing room. People would not be happy about that. If you have two sides of an equation and you just have one term on the left, one term on the right, and they both have the same base, you can drop the base and set the exponents equal to each other. You can make an equation out of the exponents by setting them equal to each other. When you have the same base, when you're just given the same base on both sides, things are very simple. So in number 14, you should try this on your own. Should be fairly simple. We've got 2 to the x plus 6 equals 2 to the 5th. What is the value of 2 to the x? So what are we going to do? We're dropping the base. We are going to set x plus 6 equal to 5. X plus 6, exponent on the left, 5, exponent on the right. We set them equal to each other. We're going to subtract the 6, we get x equals negative 1. Careful, they are not asking you what x is, they are asking you what 2 to the x or 2 to the negative 1 is. And remember, we can do the relocation method here, we can do the reciprocation method. I am going to, what did I do? I don't even know what I did. I guess I did the reciprocation method. 2 over 1, we reciprocate, we make the exponent positive, and we get 1/2. So the answer to example 14 is 1/2. Now, in terms of solving exponential equations using common bases, so in example 14, obviously we had the same base on each side of the equal sign. Things were fairly self-explanatory there, but if we see that the bases are not equivalent, for instance, if you see a base 2 and a base 4, what you may need to do is you may need to take the 4 and write the 4 as 2 squared so that you now do have common bases. That's what we mean by common bases. It means making multiple terms have the same base by writing a certain term as some number to some power. You will see how this all works in these steps here. So let's start this off. So what we're going to do is we're going to look at the bases. We're going to determine which common base can be used. In this case, clearly, we're going to be using a base of 3. 9 can be written as 3 squared. 27 can be written as 3 cubed. So we're going to be rewriting these bases using the common base to an appropriate exponent. Here's how we do that. We're going to write a parentheses, and we're going to put a 3 squared in it. Again, I'm just writing the 9 base as 3 squared, and then I've got that exponent outside that set of parentheses. On the right-hand side, we are just going to do 3 cubed. I don't really need parentheses there because there's no outside exponent like there is on the left. So now we have 3 squared to the 3x minus 2 equals 3 cubed. Now we are going to, as it says in step 2, use exponent rules to simplify some stuff. The way that we simplify here is by distributing that outside exponent to the inside exponent. This is a power to the power, or parentheses, exponents in parentheses situation here. So distributing the 3x minus 2 to the 2, that is, I'm going to write this out in 2 steps so that I don't make any careless mistakes here. So I'm going to do 2 times 3x minus 2. Over there on the right, I still have 3 cubed. The 2 times 3x, so this is 3 to the 6x, and then 2 times negative 2 minus 4 equals 3 cubed. And now I have, of course, same or common base on each side. I can apply my drop the base rule, set the exponents equal to each other. 6x minus 4 equals 3, plus 4 plus 4. I get 6x equals 7. I divide both sides by 6, and I get x equals 7/6. That is what the question was asking. We should have circled that. So that is how we use common bases and some of our other exponent rules to get to a point where we can drop the base, and set the exponents equal to each other. We're going to do a couple of examples that deal with common bases, and then we are done. In example 15, again, you might want to try both of these on your own and then come back and watch me work through them. 16x to the a equals 2x to the a. For all positive values of x, what is the value of a? That's what they want, value of a. Clearly, we're going to be using a common base of 2 here. 16 can be written as a base of 2. We've got a, I'm sorry, actually we have, these are not bases. This one's a base. This guy is not a base. This is a coefficient. But because we have that coefficient of 2, most likely we're going to be wanting to rewrite that 16 as a base 2. So how are we going to do this? We are going to do 16 gets rewritten as 2 to the 4th. I'm going to put another set of parentheses here. So that 16 is the 2 to the 4th there. There's that x, and then we have the a outside. Now we, on the right, still have 2x to the a. So over here on the left, I'm going to now drop those parentheses, 2 to the 4th x, and to the a. That is supposed to be an a and not a 9. Equals 2x to the a. My a's are looking a lot like 9s. That's dangerous. I'm going to change those. So now distributing that outside a to the inside exponent. So that's 2 to the 4a. Remember, we multiply there. 2 to the 4a times x to the a, x to the a. And that has to equal 2x to the a, 2x to the a. We can divide both sides by x to the a to get rid of the x to the a's, and now we have 2 to the 4a equals 2. Dropping the base, remember there is a unwritten 1 over here. Dropping our bases, we get 4a equals 1. We divide by 4, we get a equals 1/4. Is that what they were asking us? Yes, it is, and we're done. A equals 1/4. So again, we just rewrote the 16 as a base 2, 2 to the 4th. Applied some of our exponent rules, and we got a nice neat answer. Finally, number 16, example 16, solving exponential equations using common bases again. So what are we going to do here? We are going to first of all read the question. 2x equals 3 plus y. What is the value of 9 to the x over 3 to the y? It's right away. So first of all, let's circle this. Right away should be clear that we're going to be using a base 3 in this particular case. So I'm going to rewrite that numerator. Remember, parentheses under the original exponent. I'm going to rewrite that numerator as 3 squared to the x, and we still in the denominator have 3 to the y. Applying exponent rules, multiplying the outside exponent by the inside exponent, I get 3 to the 2x over 3 to the y. Now, what I've got to be able to see is that I'm dividing two terms that have the same base, different exponents. What do? I subtract the exponents. 3 to the 2x minus y. Now, as of this point, some students are wondering where the heck to go, but where you go is you've got to use this first equation, which we haven't used yet. And if you notice, we can actually rearrange, we can manipulate this equation by subtracting y from both sides to get 2x minus y equals 3. 2x minus y equals 3. So now I can rewrite over here, I can substitute 3 for 2x minus y. Again, 2x minus y equals 3 from this equation. 2x minus y equals 3. So now I've got 3 cubed, and now I've got 27. That is it for exponents and radicals. I know it was a lot of information. Exponents and radicals are fairly commonly tested on this test. As I said, very frequently rational exponents, negative exponents. A lot of these little quirks, these little peculiarities will be tested. Really good way for College Board to trip up students. Not very nice, but it is a good way. So that is it for exponents and radicals. Make sure you are very familiar with all this information. If you are not, obviously review it, ask your tutor, make sure you are solid on it